All right, so in this video, we're going to look at a little bit about the relationship between Venn diagrams and set notation. Set notation is one of those things that crops up periodically in different contexts, but particularly in places like, discrete math, of course, but also sometimes in statistics and probability, depending on how sort of mathy the approach to the subject is, the mathier it is, the more likely you are to encounter set notation. I originally thought about this in terms of a probability statistics course for engineering students, where they kind of went over this very quickly, but they assumed that the students would catch on without a lot of explanation. So I wanted to kind of go over the relationship. It can be really useful to think about sets and Venn diagrams together, because Venn diagrams are kind of a way to visualize set relationships. And so that can be a really useful tool for sort of understanding, particularly probability concepts. So let's start out with the basics. So in our visualization here, we have the Venn diagram and just set A. So the box around this is, think about this as the universal set. And then inside the universal set, all things that are conceivably possible, we have an event we're calling A. And then inside set A would be all of the things that are contained in A. But as you can see, set A is entirely inside the set of things that are possible. Now, the complement of A, now there's a whole bunch of different notations for the complement of A. I have seen like probably 4 or 5, maybe 6 of them, 6 different ways to notate the complement of a set. And again, it depends on the book. Some textbooks will use this AC notation. Some will use the tilde key, which is that if you go to the right of your one key on your keyboard in standard layout, if you hit shift, that's the tilde key. I have seen sort of a straight line and a hook over it, again, in front of the A set. I have seen A with a bar over it representing the complement. There's so many different ways to represent the complement of a set. AC is the notation that was used in the text that I was using at the time. But again, every text is going to have a little bit different notation. And so you need to know what the standard notation is in the textbook you're using and what your professor is using. Because again, for some reason, there is no standard for this notation. But the complement of a set, sometimes this is read as not A, is basically just everything that's not in A. So it's in the universal set, but it's not in the set A. So everything outside A. The idea is really simple. Why they haven't come up with a standard notation, it's, hard to know. Now, if you are talking about elements inside of a set, then we use this epsilon character to represent in. This is sometimes read is an element of, but sometimes that, again, math people are being lazy. That's why it's an epsilon. It's an element of, but usually we just read this as X in A. So X is an element of A, means it's something inside set A. So again, if A is the set of all Americans, then X is a particular American. If we want to say that something is not in A, then we put a slash through that same notation. So the slash, not equal to, not less than or equal to, etc. The not slash. So X is not an element of A, means that X is in the universal set, but it's in the complement of A. It's not actually in A. Remember that A and the complement of A are mutually exclusive sets. We'll come to mutually exclusive in a moment, but there's no elements in common between the two sets. So you're either in A or you're in not A. Now, sometimes we use Venn diagrams to sort of organize information that where we have lists of values. So for instance, if this is all, the universal set is all numbers between 1 and 10, all integers between 1 and 10, then the even ones are in set A, and we can write these out. X is an even number between 1 and 10. We can write these out in words or in, again, sort of set builder notation, but the even numbers between 1 and 10 are 2, 4, 6, 8, and 10 inclusive. And then all the odd numbers are in the universal set, which was all the numbers, not just the even numbers, but all the numbers between 1 and 10. And so those numbers are not in A, so they go in the universal set outside of A. Now we also have this subset notation, and essentially you need to be a little bit careful in some contexts. Some books will distinguish between these two notations and some will not. If you have a book which distinguishes between these, then here B is a subset of A, which could be equal to A, or B is strictly a subset of A, which means it's less than, essentially the elements are all the elements of A, possibly minus, and one of them is left out. So it's strictly less than A. So they're kind of like inequality notations in that sense. But in most cases, you will use, most textbooks will use these interchangeably. It's most of the ones I've encountered. I have encountered ones that have a specific distinction, but most of the textbooks I have encountered will treat both of these as synonymous, whether the underline is specified or not. B is a subset of A could mean B has fewer elements than A, or it could mean that B and A have identical elements. But a subset relation is that all the elements in B are contained in the set A, which is another reason why they don't necessarily make that distinction between like sort of strictly less than a proper subset versus just a subset generally. The reason is because often the way that this definition is the subset definition is described is that they're describing it as all the elements in B are contained in A. And that doesn't actually distinguish between the case where B represents only some of the elements of A versus whether B represents all of the elements of A. You're simply saying all the elements in B are also in A. And so thus, sometimes the lack of distinction. Now, a syllogism is a kind of relationship between sets and elements in a set. And so I've just illustrated this here. There's a famous one: all men are mortal. Socrates is a man, therefore Socrates is mortal. So we have the universal set, all things. We have a subset, mortal things. All men are mortal means that men are a subset of mortal things. And Socrates is a man means that Socrates is in the set of men. And therefore, if Socrates is in the set of men and men are a subset of mortal things, then Socrates is also an element in the set of mortal things. Okay, so this is one way of illustrating that the idea of the syllogism. A and B are disjoint, means that there's no overlap in the two sets. Disjoint is the same thing as mutually exclusive. If there is no overlap, we can draw them separately. Sometimes you'll see them drawn with a potential overlap, but there's no elements listed in that intersection. That is the same thing. But if we're just illustrating this idea of that they don't have anything in common, we actually don't allow for the overlap. But if you were to again, sometimes you build Venn diagrams without really knowing how they're related. And then if you, after you finish building the diagram, you find out there's no elements in the intersection, that is also going to tell you the same thing, that they really don't have any intersection. There's no overlap. If you draw them typically with an overlap, and again, we're just thinking about the sets here, we're saying that they're not disjoint, which means they're not mutually exclusive. They do potentially have elements that are in common. Now we have some other set operations that we can perform, like unions and intersections. And so the union of A and B is going to be all the elements that are in either A or B. So I've colored all of this blue because everything in either A or B or in the overlap, those are all included in A union B. In the case of intersection, this is the intersect. We want all of the elements that are in both A and B at the same time. So only the things that they have in common. So I've only colored in this overlapping region. Again, if this overlapping region is empty, then they're essentially mutually exclusive. But if this set is not empty, then they're not disjoint. They're not mutually exclusive. So I've done some examples here with the letters of the last name McCall and all the letters of the last name Clayton as our two sets. So in this case, the letters in the name McCall are M, C, we don't list C twice, A and L, we don't list L twice. And then all the letters in Clayton were CLAYTON. And so the letters that they have in common are ACL. And then the letters in the union are all the letters that are listed inside the blue or the green or the cyan overlapping regions, MACLYTON. And then all the letters in the universal set are just all the letters in the English alphabet in this example. And so all the letters I haven't used are in the universal set, but outside both A and B. And so my union is all of these, and then my intersection is just these three. And then I could also use this diagram to do things like the complement. What is the complement of set B, for instance? It would be all of these plus M, for instance, and so on and so forth. Now, there's one additional set notation that I'm going to mention here, which can be really useful, but it is one of those things that you can construct it using other concepts, so it's not always covered, but sometimes it is. And so I mentioned it here, which is A minus B, and basically this is A intersected with B complement. And essentially what it does is it takes any element that's in B and removes it from A. So any elements in the intersection get tossed out. So it's only the elements that are in A that are not shared with B. And so that's what this looks like the crescent moon shape. Now, this yellow region is the complement of B, right? So again, that would include things that are in A, but not B. So that's yellow. And then the things that are in A, I made red. And so where yellow and red overlap, you get orange. And so the orange is, again, that intersection, the overlap, that's where you get A minus B. So these notations are completely identical to each other, but this is built from sort of those more basic principles that we talked about earlier. And but again, sometimes you'll see the special notation A minus B because it is sort of more useful sometimes to think about it as, well, I'm just taking the intersection out. I'm taking out things they have in common. It's easier for us to process And so even though it's not strictly necessary, it is often included. Now, you can also do these Venn diagrams with more than 2 sets, and that's usually where it can be really helpful. So I'm just going to do a couple of examples. A union B union C is all the elements that are in A or B or C. Because these are all unions, they're kind of like addition signs in some sense. And so you don't have to specify which 2 you're going to intersect first with, and then the third one, because it doesn't matter. And then same thing for the complement. A intersect B intersect C is all the elements that are in that A, B, and C all mutually share. And then, of course, you can combine them in different ways. And again, what I've done with the shading here is I've colored C all yellow, and then the intersection of A and B, I've colored that green. And then where they overlap would be their intersection, and where they, if it's a union, it's any part of the shading. So in this example, all of the shaded components, the intersection of A and B and all of C, are all included in A intersect B union C. Whereas if these were all intersections, it would just be like the one above, it would just be the overlapping portion. But because this is a union, it's actually any part of this shading right here. And again, notice I essentially combined these in 2 stages at a time. So I first figured out where A intersection B was, and then I found out where C was, and then I decided how to either overlap them or collect them all together because of the last item. Now, when you're using combinations of operations like this that are different from each other, you do have to put in parentheses in order to indicate the order of operations, because it will matter, because intersection and is kind of treated like multiplication in the sense that you should do it first. And union is treated like addition, so you should do it after intersections if you don't have the parentheses specified. But so generally for 3 elements, if they're not all the same operation, you should specify the parentheses of which to do first. Otherwise, it could be considered ambiguous. Now, we won't do any examples with 4 sets. Part of the issue with 4 sets is you actually you can't just use circles anymore. In order to actually cover all of the combinations of intersections, you actually have to change the shape of the sets that you're using. They can become quite complicated as you increase the number of sets. There are some nice websites out there, if you Google for them, that will actually build your 4 sample, 5 sample Venn diagrams. I think I've seen up to 11. But this is the relationship between Venn diagrams and set notation. Again, the idea here is that you have a tool to help you visualize these relationships. When you start sort of getting out of this sort of abstract, simple case, and you start getting into real world problems and things like that, it can be helpful. And we're going to see in another video how these things relate to the ideas around probability.